Hello and welcome back. This is the first of three lectures on Chapter 9 material. Now, Chapter 9 introduces the concept of momentum. Now, we actually wrote down the equation for momentum, I want to say back maybe in Chapter 6 or 7, somewhere around there. And momentum is a vector. It's defined as an object's mass times its velocity. Now, this is a little difficult to visualize. We can visualize things like forces and we can visualize things like velocities and stuff like that. But momentum itself is more of a conceptual construct. Now that said, it turns out that if you go back and you think about, the material that we talked about when we first started learning about forces, specifically Newton's second law, we had written down a version of Newton's second law that looks like this. Now, Newton, when he actually came up with his three laws and he published them in the Principia, didn't actually write down an equational form, but the wording that he used didn't suggest this per se. It actually suggested this. Forces cause objects to experience a change in momentum over time. Now, what's the difference between this and this? Well, this right here is a version of force that's better suited for constant mass. Now you can see if I were to expand out acceleration as dv dt, and then because mass in this particular situation would be constant, pull the m inside the derivative. Whoops. Actually do that. That you have momentum inside. But in general, mass may not be constant. So this ends up being a better suited version for Newton's second law. Now, if you take this and you massage it a little bit, specifically, I want to take and put dp on one side and then put f times dt on the other side. We're going to integrate both sides. We'll say from your initial momentum to your final momentum, whatever that might be. And on the right-hand side, we'll integrate from your initial time, which I'll call t naught, to your final time, which I'll call t. On the left-hand side, you get the change in momentum. Now, this actually has a formal name. It's called impulse. And often it's written as just a j vector. This is actually, I believe, called the impulse momentum theorem. Now, that said, impulse itself, again, which is your change in momentum, is what you get when you look at how forces are spread out over time. Okay. So, just for the sake of argument, I'd like to consider a situation in which your force is constant. So, if your force were constant, then the integral on the right-hand side actually is pretty easy to write. Okay, you can pull the force out, and then you're just integrating dt from t naught to t. Now we know when you integrate this, you get delta t. All right, and perhaps this is a better way of getting an understanding of what momentum might mean. So I want you to imagine boxing. Okay, so you had a problem in a previous chapter where you looked at the behavior of a boxing glove that had padding in it. Okay, we'll pretend this is a glove versus just bare knuckles. All right. Now, so what the pad does is to extend the contact time out. So it actually creates more time for impact. So think a sharp hit versus a sort of squishy hit, if you want to think of it like that. Now, so imagine, this fist is coming in and maybe it's hitting somebody's head. You know, maybe that person's head's initial velocity is 0. Whether you hit it from a bare knuckle standpoint or whether you hit it with a boxing glove, the head's going to snap back with some final velocity, which I'm going to call VF. Okay. So in both situations, the final velocity of the head's the same. Okay. So what that means is regardless of what's going on, since momentum is m times v, the change in momentum in both situations via bare knuckle or with a glove is the same. But look at the right hand side. So like I said, what gloves do is they extend the collision time out. So if the left hand side is constant, it doesn't change between the situations. Okay. And you make delta t here get bigger. You extend the collision time out. What happens is the average force that this person's head's going to experience gets less. It goes down in order to make this balance work. Okay. On the other hand, a sharp hit without this padding right here is a very short amount of time. And if this is very small, that means that the force is very big. Okay. So the way I personally understand momentum or get a feel for it is through this relationship. Okay. Momentum is sort of how hard you can hit from a boxing standpoint. Okay. But it's not, because how hard implies force. Now, that said, another use for momentum, or rather impulse, this particular equation, would be to look at situations like this. Now, this is a modern car. Modern cars have crumple zones. All right. If you look at this place right here, if you look at this right here, these two areas right here are crumple zones. What that means is they act like the padding in that boxing glove. So if your car gets into a collision with someone, we'll say in the front's hit, what it does is to crumple like the glove and cause the duration of the collision to go up. And what that means is that the average force felt by the car and also by the person on the inside goes down. Okay, that's the same purpose that that airbags have. Okay, airbags sit between a person and the steering wheel. Okay, and what they do is they squish. Okay, and as a consequence, they extend the collision time as well. So between crumple zones and airbags, what that does is to greatly reduce the amount of force that you feel in the car during a collision. Now, prior to designs like this, like say back in the 70s or in the 60s, there were no crumple zones. And it was entirely possible for somebody to get into a wreck and have the engine end up in their lap and kill them. All right. And it's because of these designs right here. What that does is to minimize the chance of that happening. Now, so just as an example, I'd like to work this problem right here. We have a car that's initially traveling at 35 meters per second. It comes to rest in 2.5 seconds. What is the average force felt by someone inside the car? Assume that the mass of the car is 1,250 kilograms. Okay, so now where does this force come from? Well, as you slam on the brakes, there's friction between the wheels and the ground. That's what's slowing you down. And that is the origin of the force that's causing you to experience, what's going on. Now, so that said, let's draw a picture. Oops. Here's your car. The initial velocity of your car here is to the right. It's 35 meters per second. Okay. You come to rest, we'll say somewhere over here. So here's your initial position, here's your final position. At this point right here, your velocity is 0. Now, it has taken you a total time of 2.5 seconds to come to rest, and the mass of your car is 1,250 kilograms. Okay, so now you are sort of as a consequence of all this stuff, you are part of the car. We're assuming here. So the impulse for constant force looks like F vector times delta t. Okay, so if I want to know what the force is here, it's going to be delta p over delta t. And again, this constant force, right? So here, your change in momentum would be your final momentum, which I'm just going to call p, minus your initial momentum. And delta t here is just going to be t. So what's your initial momentum look like? Well, that's going to be your mass times your initial velocity. And what's your final momentum going to look like? Well, that's going to be your mass times your final velocity. But look, your final velocity is 0. So that goes away. Okay. So based off of what we have here, this would be m times v naught vector over t. The mass is 1,250 kilograms. V naught vector is 35 meters per second in the x-hat direction. Okay. And then you have a negative sign here over 2.5 seconds. So when you do this, you get divided by 2.5. You get about 17,500 newtons in the x-hat, or the minus x-hat direction, rather. So here's your answer right there. Now, so that said, in general, your force may not be constant. And there are a couple of different ways that you can deal with forces that aren't constant. If your force is a function of time, whoops, that actually turned out relatively good for what it was. If your force is a function of time, then you're okay. Your change in momentum, in that case, all you do is you just integrate that force over time, and you're set. But as we've noticed, the vast majority of our forces are functions of time, especially the conservative ones. The conservative ones typically only depend upon, position. So one way you can handle a force that is a function of position, because you have this time integral, would be to average it. So how do you average it? Well, you turn to the fundamental theorem of calculus. So the fundamental theorem of calculus says that if you want the average of a function, okay, what you do is you integrate it, we'll say from a to b, and then to average it, you divide by b minus a. All right, so if you take and you follow this approach right here, what this does is to give you the average force, which would be constant. This gives you an average. And as a consequence, you can now the version of the impulse that you would use would just be whatever your average force is here, times the change in time, just like what we did before. Okay, so as an example, consider a spring. Okay, so the force due to a spring is a function of x, or position, the stretch. And it looks like minus k times x times, x hat. Okay, if you think of, just a simple one-dimensional force like this. Do it like this. So maybe it's your standard spring attached to a wall going back and forth type thing, right? Okay, so now imagine a situation where you've stretched your spring. We'll say to here. We'll call this x naught, and then you let it release, and this is your position x. We're not going to take it to the origin. We're just going to put it right here because we want this to be arbitrary. So what you would do here to find the average of what the spring force is. So we'll say spring force average. Okay, would be to integrate it. From x naught to x. And then following the fundamental theorem of calculus, this would be x minus x naught. Okay, and this should give us the average. So, if you take it and you plug that in here, this is what we'd be integrating. And so we're going to pull out the minus k x hat because those are constants. And you're integrating x dx, which we've done many times. And so when you do that, you get 1/2 x squared evaluated from x naught to x. And if you plug those in, you get minus k x hat over x minus x naught times 1/2 x squared minus 1/2 x naught squared. Now, if we sort of clean this up a little bit, what you're going to end up with this is, from a vector standpoint, the average. This is very frustrating writing. Average vectors here. The average vector is going to look like this. 1 over x minus x naught times 1/2 k x squared minus x naught squared in the x hat direction. And then you have the minus sign that sits out in front, like that. So this right here would be something that you could plug in, dealing with a spring. And this is just a number. So, you put your initial and your final positions in there, and that's going to give you the average force between those two places. Okay. On the other hand, what if you have a force that's a function of time? Well, like I said, you just do the integral then. So, imagine a force that looks like this, maybe. I don't know, F naught times e to the minus t over tau x hat. Okay, so it's just some sort of exponentially decaying force. So, the change in momentum in this particular situation would be if you, assume we'll start at 0 and go to t. So this right here is what we'd be integrating. And F naught and x hat are constants. And so if we do just a quick substitution, and we say that u is equal to minus t over tau, then du is going to equal to minus 1 over tau dt. And every time I see a dt, I should put a minus tau du. All right. So if you take and look at your limits of integration, when t is equal to 0, uh, u is equal to 0. When t is equal to t, u is equal to minus t over tau. So our limits of integration have changed this way. All right. Now we're integrating e to the u, which is very easy to do. And dt is minus tau du. So if you pull all the stuff that's constant out now, you have minus f naught tau x hat here, and you're integrating from 0 to minus t over tau, e to the u du, and this is just e to the u. Evaluated from 0 to minus t over tau. So your change in momentum in this particular situation would be, minus f naught tau x hat e to the minus t over tau minus 1. Or if you run the negative through, which is typically how this is written. So now you can see how it decays. As this gets bigger, this right here gets smaller, so you can see the force or the change in momentum do its thing here. Okay. Now, so just as an example. Now, that said, what I would like to do is to take this one for the spring, and we're going to apply it. So let me just copy that real quick, and then we'll go over here and we'll paste it right here. And I've got this problem right here. What is the average force of a spring that has been stretched or compressed and released? Using this result, what is the impulse of a mass of 0.22 kilograms connected to a spring that has been stretched 15 centimeters beyond its equilibrium point and released from rest? The spring has a spring constant of 520 newtons per meter, and the points we're considering are its initial position and the equilibrium position. How long does it take for the mass to get to the equilibrium position? Okay, so we've already done the work to find the force. It looks like this right here. So let's draw this picture. So here's the origin. Actually, let's not make that the origin. This will be the wall. Like that. Here is our spring attached to the wall. Like that. Here's our mass on the end. Like that. And then we're going to take and we're going to put our, we'll say our equilibrium position is something like this maybe. So right there, that's going to be where, where our 0 is. This is where our y-axis is. And this is x. Okay. So here's our mass. Now what do we know? We've been given that the mass on here is 0.22 kilograms. We're given a spring constant of 520 newtons per meter. This thing has been stretched 15 centimeters beyond its equilibrium point and it's been released from rest. So that tells us our initial velocity is 0. Also tells us that our initial position is 15 centimeters or 0.15 meters. Now, the final position is at the equilibrium position, which we know is 0. Okay. So what are we trying to find? We'd like to find the amount of time that it takes for the mass to get to this equilibrium position. So we'd like to find t. Okay. Now, so what I'm going to do in order to solve this is to use both energy and also our equation for impulse. And the reason why I want to do that is because if we're going to find time, the way I'd like to approach it is through the the impulse equation right here. So we'll be able to find the average force here. We can solve for time, but we're going to need the change in momentum. Now we know what the initial momentum is. It's going to be 0 because it starts off at rest. We know what its mass is. What we need is the velocity of this thing as it crosses the center line, okay, because that's the second point of consideration. Now, to do that, let's just consider our initial energy, which would be our initial kinetic energy plus our initial potential energy. And our initial kinetic energy is 0 because it's not moving. So the energy that's stored inside the spring is going to be 1/2 k times x naught squared. Now, when it crosses the equilibrium position here, the energy that we have is going to be k plus u. But we know at the equilibrium position, since that's 0, okay, and the potential energy for a spring has this form, there is no potential energy there. Okay, so our final energy is just going to be 1/2, k mv squared. There we go. And these are equal. So using conservation of energy arguments here, we have 1/2 mv squared is equal to 1/2 kx naught squared. Okay, so from this, we'll be able to get your final momentum. All right, you can solve for v. V would be canceling out the halves. The square root of k x naught squared over m. Okay, or you can do something else. All right, now, so what's this other thing? I'd like to point out the fact that kinetic energy looks like this: 1/2 mv squared. Now imagine taking your kinetic energy and multiplying it by 1 in the form of m over m. So if you do that, what you end up with is 1/2 mv squared over m. Now this right here is the magnitude of your momentum. This would just be p without the vector sign. And one form, in fact, many times it's a preferred form for kinetic energy, is p squared over 2m. All right, so you could find your final v, or you could find your final momentum by noting the fact that p squared over 2m, which is the same thing as kinetic energy, is equal to 1/2 k x naught squared. So in this case, if you multiply both sides by 2m, you get p squared is equal to m times k times x naught squared, or your momentum is equal to the square root of k times m times x naught squared. So this is another way that you could do it as well. In fact, I'm going to use this. So here's what we have. We have our average force. Now we can find the change in momentum. All we have to do is to find out what delta t is. Okay, so let's go ahead and solve for the average force. It is minus 1 over x minus x naught times 1/2 k times x squared minus x naught squared. Our final position is 0. That's 0. That's 0. A negative times a negative is a positive, times a negative is a negative, which makes sense. Our force is pulling us to the left. Minus 1/2 k x naught squared over x naught in the x hat direction. This kills this off right there. So your average force is minus 1/2 k x naught in the x hat direction. Okay? So delta P is equal to F vector times delta T. Whoops. So delta t, let's just go ahead and plug in the vector form. Delta p is your final momentum minus your initial momentum. Your initial momentum is 0 because it's not moving. Your final momentum has us moving to the left. Moving to the left, 1/2 k x naught. Oops, sorry about that. Copying stuff verbatim. Moving to the left here, minus the square root of k m x naught squared in the x hat direction. That's this. On the right-hand side, we have our force, minus 1/2 k x naught x hat times delta t. Now, we can get rid of the x hats. We have a negative here. We have a negative here. You have a square root of x naught squared. This is just x naught. This is x naught. That goes away. Okay. So, on the left-hand side, we have the square root of k times m. On the right-hand side, we have 1/2 times k times delta t. Now, if I multiply through by 2, then I divide both sides through by k. I'm going to clean this up a little bit. The square root of k over k is the same thing as, this is actually the square root of km over k. It's the same thing as the square root of m over k. You have a 2 here. When it comes in, it'll become a 4. So this is how long it's going to take for it to go from this position over here, where it's been stretched, to the equilibrium position. How long is that? Let's just go ahead and do it here. Since we got our information right here, it is the square root of 4 times m, which is 0.22 kilograms, divided by k, and k is 520 newtons per meter. If you do that, you get 0.0411 seconds, something like that. If you want to do sig figs, we have 2 here, we have 2 here. There you go. Okay. So a little more convoluted, sure, but impulse is a nice thing. So that said, what I'd like to talk about now is not impulse. What I'd like to talk about is conservation of momentum. So we've talked about conservation of energy in the past. We saw how useful that was. And there is an equivalent theory for momentum. And one of the nice things about it is that it allows us to deal with how objects interact with each other without dealing with some of the details of interaction. As the saying goes, the devil is in the details. And when it comes to collisions, that is very much true. So, I want you to think of 2 objects. I'm not very creative right now. Object A and Object B. And I'd also like you to think about Newton's third law. Now, Newton's third law says that if Object A exerts a force on Object B, Object B is going to exert exactly the same force back on A. It's just the direction has changed. So let's call this force right here the force of A on B. And this return force the force of B on A. Now, Newton's third law says these forces are equal but opposite. Okay? Now, so before I go any further, we're going to consider only an isolated system. Now, what do I mean? Well, if you remember, when we talked about energy, specifically when it's conserved and when it's not, one of the things I had mentioned then was that if you consider just the problem and you don't consider anything coming from the outside or any of what's going on in the problem leading to the outside, energy typically is conserved. And as I'd mentioned, when you have situations like, say, frictional forces take kinetic energy and turn it into heat energy and sound energy, potentially even light energy. Those, we say, leave the system or in places that are not accessible to us to get the energy back, at least not 100% of it. When we deal with conservation of momentum, the condition that we have for it to work is that you can't have any external forces from the outside of the system. For example, let's pretend that I was thinking about this interaction happening on the inside of a box. So there's a box right here. We'll say, let's add a little bit of dimensionality to it. Maybe it looks like this. So here's your box. Here's your particles inside the box, your objects, A and B, interacting with each other. If I were to take this box like this and shake it, what I'm doing is I'm introducing outside forces in. And in a situation like that, we can't competently talk about conservation of momentum. So we're dealing with an isolated system. And by isolated, what I mean is that there are no forces from the outside coming into the problem to screw around with stuff. Now, in a situation like that, what I'd like to do is to rewrite our forces as changes in momentum over time. So, the force of A on B, we can write as the change in B's momentum over time. Because that's what's going on. A exerts a force on B, and B is the one that's experiencing the change in motion, or the change in momentum. The force of B on A, well, that's going to be B affecting A's momentum. Okay? Now, here's the deal. If A spends 20 seconds interacting with B, B is going to spend exactly the same amount of time interacting with A. As long as they're in contact with each other, as per Newton's third law, they're exchanging forces. So the amount of time that these things experience interacting with each other is the same. So if I were to think of this as being a change in momentum like this, the delta t's would be the same. Okay? So now let's write this, as Newton's third law here. The force of A on B causes B to experience a change in momentum over time. B, as a consequence, returns an interaction onto A. The interaction times are the same. So what this turns into on the left-hand side would be B's momentum after the interaction minus B's momentum before the interaction. So to rewrite that, so I can actually put a B there. The momentum of B after the interaction minus the momentum of B before. On the right-hand side, I have a minus sign and a change in momentum in A. The momentum of A after the interaction minus the momentum of A before the interaction. You'll notice that we're not talking about the guts of the interaction itself. We're not talking about the act of colliding. We're talking about what happened before and what happened after. Now, what I'd like to do is to move everything that deals with a final situation to one side, we'll say it's the left-hand side, and everything that deals with an initial thing to the right-hand side. The negative here hits this negative and makes it positive. This one it moves over here is going to be positive. This one it moves over here is going to be positive as well. And when I do that, I get the following. PA plus PB is equal to PA naught plus PB naught. Oh, look at that. So what this says is the following. If you take your two objects and you look at their masses and their velocities before they start interacting with each other, and you add those momenta up as a vector, these are vectors, then the vector that you get does not change before or after the collision. This is conservation of momentum. Now, I want to be very clear. This is what's called linear momentum. When an object travels from point A to point B in space, like this, we say that it translates. That's the type of momentum that we're looking at, translational momentum or linear momentum. There are other types of motion as well, which we'll be getting into very, very shortly. For example, what if your object rotates about a point? Well, there's a type of momentum that's associated with that. There's also a type of energy that's associated with that motion. This is rotational motion, and the momentum that's associated with this is called rotational or angular momentum. Okay, it's also the reason why if you are in, one of those spinny desk chairs and you spin in a circle and you pull your arms in, you go faster. And we'll be talking about that. But nonetheless, this right here is incredibly important. This is conservation of momentum. And much like conservation of energy, it's something that you should write down in your notes and put a huge star beside to remember, because it is something that you will not stop seeing. It's incredibly important. Now, so that said, there are two basic types of momentum conservation problems. So two basic types. These are idealized, okay? So we call them perfect. So you have what's called a perfectly elastic collision. And then you have something called a perfectly inelastic collision. Now, so an elastic collision is when they hit and they bounce off. For example, if you ever shot pool or played billiards, if you, hit the cue ball with your stick into an 8-ball or a 9-ball or something like that, if you don't use any English, then that type of collision is close to being inelastic collision. I say close because perfectly is idealized. In truth, with the exception of very few specific examples, most collisions sit somewhere in between. Now, so a perfectly inelastic collision is one where they hit and stick. You take a handful of mud and you throw it against a wall and it hits and splats. That's a perfectly inelastic collision. Now, when it comes to doing problems, these are the easiest to do, and this is actually uh, what I'd like to talk about a little bit today. Okay. Now, I'm not going to tell you quite yet what the other difference is between these two types of collisions. I'm going to use an example of an inelastic collision to show you. Okay. So, go down here. We want to work this right here. A person of mass 75 kilograms wears a bulletproof vest and is shot in the chest with a .308 bullet. Now, .308 is a rifle round. It's used sometimes in the military for sniping. People who hunt use it a lot. The bullet has a mass of 11 grams and travels with an initial speed of 806 meters per second. We're going to assume that the bullet hits the person and sticks to the vest. And what I'd like to know is what the person's recoil velocity is. Okay, so that said, the way you do conservation of momentum problems is you look at the situation before the collision, before the impact, and then the situation after. So this is going to be a before picture, and this will be an after picture right here. All right, so here's the y-axis, here's the x-axis, here's the y-axis, here's x. This is before, and this is after. Okay, so before, what you have is a person, we'll say, standing at the origin here. So here's a person wearing their vest, and then here's your bullet traveling to the right like this. Your bullet, which I'm going to say has a mass of m sub b, okay, 11 grams. We'll have to convert that. And it also has an initial velocity. It's the bullet's initial velocity. It's to the right. It's 806 meters per second x hat. Now your person has a mass of 75 kilograms. But your person's initial velocity is 0. So the bullet hits the person's vest. Let me put some Batman effects here. Bam. The appropriate collision graphic like that. And then afterwards, what happens is you have a person with a bullet sort of stuck to the vest, if you want to think of it like that. Now, so what that means is that the velocity of your person after the collision is going to be the same as the velocity of the bullet after the collision. Okay, now I'm just going to call that V. Now, why is that? Well, they're stuck together, so as they recede back this way, they're both receding back with the same velocity. Okay, so now what are we given? So before the collision, we know the mass of the person is 75 kilograms. The mass of the bullet is 11 grams, which is 0.011 kilograms. We also know that the velocity of the bullet initially, is 806 meters per second in the x-hat direction. We know the velocity of the person initially is 0. Now, what are we trying to find? The recoil velocity, V. Remember, the bullet and the person are going to have the same velocity. Now, so we know what we're given. We know what we're trying to find. there are no external forces that are acting on our system, which means that if I look at our initial momentum, the total, that's going to equal to the final momentum total. So what's our initial momentum equal to? Well, we have the initial momentum of the bullet, and we have the initial momentum of the person. But here's the thing. The person isn't moving initially. So if you think of momentum being mass times velocity, no velocity means no momentum, which means the person's initial momentum is 0. So the initial momentum of the system is just the bullet, which is the bullet's mass, times the bullet's initial velocity. Now, after the collision, we have the momentum of the person and the momentum of the bullet. Now, the person's momentum is the mass of the person times the velocity of the person, which we noted is going to be the same as the bullet's. It's just v. The bullet, its mass times its velocity. And if you notice, these both have the same vector, which means that it's just the mass of the person plus the mass of the bullet times v. Now, these are equal. Okay, your initial momentum and your final momentum, the totals, are equal to each other. And so what that means is the mass of the bullet times the velocity of the bullet initially is equal to mp plus mb times v. So the way to think about it is that the initial momentum of the bullet and the person, because this is an inelastic collision, since these things are sticking, okay, form a composite object after, which has one velocity. What's that velocity equal to? Well, in this situation, mass of the bullet times the bullet's initial velocity divided by the mass of the person plus the mass of the bullet. What do you get when you do this? What's the mass of the bullet? It's 11 grams. What's the velocity of the bullet? 806 meters per second in the x-hat direction. Divided by 75 kilograms plus 0.011 kilograms. What that's all about, kilograms. Sorry about that. All right. Excuse me. So what's this equal to? I get, let's see, 0.011 times 806 divided by 75 plus 0.011. 0.118 meters per second. Or if you keep the sig figs, I see 2 here, I see 2 here, I see 3 here, so 2. About 0.12 meters per second in the x-hat direction. Or, 12 centimeters per second. So what that means is that unlike all those movies that you may have seen where people get shot with guns and they go flying through windows because of the recoil, here the recoil is only about 12 centimeters per second. Now, for those of you that live here in the United States and that are taking this class, this ends up being something like, let's see, about 4.6 inches per second. So no, you don't go flying through walls when you get shot like this. The recoil is very gentle for the most part. Now, here's another example. A bus of mass 4,520 kilograms is traveling at 35 miles per hour, and it collides with a car that has a mass of 1,200 kilograms that's at rest. We'll say maybe it's sitting at neutral at a stoplight or something like that. Assuming that they collide and stick, what's the final velocity of the bus And I'd also like to compare the initial and final energy of the system. Okay, so again, we draw a picture. We have a before and we have an after. So here's our bus. Traveling to the right. Like that. Here's your car. Parked at rest. So the mass of the bus is 4,520 kilograms. The mass of the car is, that looks like a knot. The mass of the car, there, that's better, is 1,200 kilograms. The velocity of the bus initially, 35 miles per hour. We'll say in the x-hat direction. We need to convert that to meters per second, obviously. The velocity of your car initially is parked, 0. So let's get our special effects. We'll use Zot. That's a good Batman effect. So you got your bus and your car sort of zoom off to the right as a composite object. I'm not sure what you call that, a cuss, a bar, something. You got your wheels, you got car stuck on the front, we'll say. Okay, so what happens is because composite objects, both of these go flying off the same speed or the same velocity rather. That velocity is v. So what do we have? What are we trying to find? What are we given? So we're given the mass of the bus is 4,520 kilograms. The mass of the car is 1,200 kilograms. The velocity of the bus initially, now that's 35 miles per hour. If I convert that, let's see. It's about 15.64 meters per second. Okay. We're also given the initial velocity of the car. That's 0. Now, what are we trying to find? Two things. We're trying to find the velocity after the collision and also the energy before and the energy after the collision. So what I'm going to do to begin with is to solve the momentum problem, and then we're going to come back and we're going to take a look at energy. All right? So again, we have an initial momentum. That's going to be the initial momentum of the bus plus the initial momentum of the car. But if you look, your car's velocity again is 0, which means it has no momentum, which means since momentum is just m times v, our initial momentum right here is going to be the mass of the bus times the bus's initial velocity. So there's your initial momentum right there. So afterwards, we have the momentum of the bus plus the momentum of the car. That's going to be the mass of the bus times this velocity plus the mass of the car times this velocity. Or once again, the mass of the bus plus the mass of the car times v. And these things are equal. So the mass of the bus times the velocity of the bus initially is equal to the mass of the bus plus the mass of the car times the final velocity. So what's v equal to? mb divided by mb plus mc times vb naught. That's 4,520 kilograms. No. Times 15.64 meters per second in the x-hat direction, divided by 4,520 kilograms plus 1,200 kilograms from the car. And if you do that, you get let's see here, the divide by 4,520 plus 1,200. 12.36 meters per second. Now, if you convert that to miles per hour, it ends up being something like 27.6 miles per hour. Or, like 28, keeping it 2 sig figs. So what's happened, obviously, is, the bus hit the car, it picked up this extra mass, and as a consequence, the composite obstacle rolls away at a velocity that's less. So here's one answer. Now let's take a look at the energy. So in the absence of external forces, the only energy that we have present is energy that's in motion. Okay? Before the collision, there's just motion. After the collision, there's just motion. So if you think about that, that means that your initial energy would be the bus's initial kinetic energy plus the car's initial kinetic energy. But the car is not moving, so it has no kinetic energy. So it's just going to be the bus's initial kinetic energy, which would be, 1/2 mass of the bus times velocity of the bus initially squared. Now, after the collision, you have the kinetic energy of the bus and you have the kinetic energy of the car. They're both moving. That would be 1/2 mass of the bus, v squared, since they both have the same velocity, plus 1/2 mass of the car, v squared, which again we can write as 1/2 times mass of bus plus mass of car times v squared. So what I'd like to do is to just look at the initial and the final energy and can compare them. So my initial energy is going to be 1/2 the mass of the bus, which is 4,520 kilograms, times the velocity of the bus initially, which was about 15.64 meters per second. You have to square that. So what's my initial energy right here? 0.5 times 4,520 times 15.64 squared. That ends up being something like 552,818 joules. Now, so after the collision, 1/2 times the mass of the bus plus the mass of the car times the velocity squared. Now, what's the velocity? Well, after the collision, it ends up being 12.36 meters per second squared. So, what do you get here when you do it? 1/2 times 4,520 plus 1,200 times 12.36. Square that. I get 436,921 joules. Now that's interesting. So what this tells me is the energy after the collision is less than the energy before the collision. Oh. If you do the difference between them, you have a change in energy of negative 115,898, or 896 rather, joules. Okay, so keeping the sig figs here, if you wanted to, there's only two. This is a difference of about 120 kilojoules. So where'd it go? Well, that's the reason why we don't talk about the gusts of the collision. When these things collide, you have metal being bent, you have all sorts of rending, shearing, sound. Energy is lost in a huge way during an inelastic collision. So, I told you that I was going to tell you what the other difference between these two was. And that's the big thing. Perfectly inelastic collisions do not conserve energy. And that's because during the collisional process, the deformation that occurs eats up energy. Now, in an elastic collision, though, during the collision, things don't deform, presumably. And in that situation, they conserve energy. Now, we'll be using this fact next lecture to help us look at just simple one-dimensional collisions. And then we'll extend it to two-dimensional collisions. We're going to need it. Now, that said, the very last thing I'd like to talk about are rockets. Rockets, how do they work? Well, that's a good question. If you think of what you know so far about physics and stuff, let me sort of draw us a rocket here. Got some fins, we'll say, and let me hack this bottom part off. Let's have a place for the fire to leave, right? So that. Okay, so if you think about how a rocket acts whenever it takes off, you see this thing, obviously fly upwards. So you would think there's some sort of force that's propelling this thing upwards in order to make it lift off the ground. And so, where's the force coming from? Well, some people, when you ask them how a rocket works, will tell you that you're pushing off the ground in order to go up into the air. Some people will tell you that you're pushing off of the air to fly through the air. But what about space? There's no ground there to push off of. There's no air there to push off of. So how does a rocket work in space? Well, that's a good question. So it's all about conservation of momentum. Now, the fuel that you see used in a rocket, at least the conventional ones, is some sort of chemical thing. It's a chemical rocket. It could be a solid rocket booster. The fuel is solid in that case, almost like a bottle rocket. Or it could be liquid. Typically, it's liquid oxygen and liquid hydrogen. And so what you do is you stick these guys together, and then you toss in a match. And what that does is to produce a lot of heat, big explosion, lots of heat. And you also get H2O as a byproduct. You get water. And in fact, a lot of times when you see your standard, liquid fuel rocket take off, that stream of exhaust that you're looking at is actually a vapor trail. It's water vapor. That's water vapor. So, so what does that have to do with forces and stuff? Well, if you think about shooting a gun, if you've ever shot a rifle or a pistol or anything like that, um, you know that when the bullet flies out, you get a kick back. Now that's because momentum's being conserved. Okay, if you think about um, the the chamber here where the bullet sits before you pull the trigger, the bullet is at rest with respect to the gun. So your initial momentum, since both things are at rest, would be zero. But when you pull the trigger, a chemical reaction happens inside the cartridge of the bullet. What that does is to push the actual bullet part out. And as a consequence, uh, in order for the momentum overall to be zero, since the bullet has momentum to the right, there needs to be a matching momentum to the left for them to cancel each other out. That's the kick that you experience whenever you shoot a gun. Okay, and what's happening is that if you think about the seal of the cartridge right here, and you think about the head of the bullet like this, and you have all this combustion that's going on the inside, due to the gunpowder or whatever it is that is doing its thing. This combustion right here is exerting force on the underside of the bullet, and as a consequence, the bullet's exerting force back. When it finally pushes the bullet out, the bullet pushes back. Okay, and what that does is to since the cartridge is affixed inside the rifle or the gun or whatever it is it kicks back. All right, so you get the force as the bullet kicks away. Well, it's a similar thing as what's going on over here with the rocket, except instead of bullets, what you're shooting out of the back are water molecules. Okay, or if it's a solid, rocket booster, whatever particulates being shot out due to that combustion. Now, the reason why they're flying out the back is because they're hot. They're very hot. They're steam. They're superheated steam, actually. So, as an example, if you were to, we'll say, cook something in an oven, we know that before you turn the oven on, if you open up the oven door, you don't get blasted in the face by hot air. But if you turn the oven on and you open the door with the hot air on the inside, you get blasted in the face. And that's because one of the things you're going to learn in University of Physics too is that temperature is basically the same thing as kinetic energy. It's the kinetic energy, or the average kinetic energy of the objects that make something up. So here, because this is superheated gas, these little guys are leaving out like this very quickly. And as a consequence, you have, if you think of your rocket sitting at rest on a platform, these guys go flowing out the bottom, and as a consequence, the rocket recoils. So if you were to look, inside the bell right here, as these guys fly out, they're colliding, with the walls of the bell, and each collision is a lot like this, except it's elastic. And so what happens is you have a change in momentum. These guys are killing some of their momentum as they go flying out to the rocket itself. So when it hits here, for example, if this guy hit here, that's pushing it up. Okay, so it's all of this exhaust as it goes flying out that causes this thing to do what it does. And as a consequence, a lot of times they refer to the fuel inside the rocket as reaction mass. Because for every action there is an equal but opposite reaction. It's just a restatement, basically, of let's see here, of conservation of momentum. That's just a restatement of Newton's third law, where all this comes from. Remember, for every action, there is an equal opposite reaction. Same thing. Okay, so the reason why your rocket lifts off is because of conservation of momentum, and you don't have to use you know liquid oxygen and liquid hydrogen to make this work. You don't have to use chemical fuel. If you've ever seen one of those little toy rockets where you get your rocket, you've got a little thing that clips to the bottom, and you pump it up. You put water in your rocket, and it lifts off. It's using water as its reaction mass. Okay, so that's how rockets work. They don't push off the air, push off the ground. It's conservation of not angular, but conservation of momentum that allows them to lift off the ground. Now, that said, this is where we're going to stop for lecture 1. And in lecture 2, we're going to talk about what happens when you have a collision that conserves energy. Well, what happens when you have perfectly elastic collisions? And I'll see you then.